Have you ever looked up at the night sky and wondered how on Earth we know what stars are made of millions of light years away? Or how a quick, simple test can tell you if your water is safe to drink? Well, the answer is something called spectroscopy, and it's basically like having a superpower that lets us see the unique chemical fingerprint of almost anything, just by using light. So, let's start with a basic question. How do you measure something you can't actually see? It sounds impossible, right? But you probably do a version of this every single day. Just think about making a cup of tea. You can tell exactly how strong it is just by looking at the color. The darker the tea, the more tea leaves have dissolved in the water. We're going to dig into the science behind that simple, everyday observation. So that gut feeling you have about the tea, it's actually backed up by a fundamental rule of science. So let's dive into our first section, the law of light, and really get a handle on the rules of absorption.
Okay, so just like our tea, when you shine a light through a colored liquid, some of that light gets soaked up. It gets absorbed. And here's the key idea. The amount of light that gets absorbed is directly related to how concentrated that solution is. The darker it is, the more light it absorbs. It's a really simple concept, but it's the bedrock of this entire field. Now, this relationship has an official name. It's called the Lambert Law. This is the scientific rulebook that tells us exactly how light is going to behave when it passes through something. And it says that the amount of light absorbed depends on two key things. One, the concentration of the stuff in the liquid, and two, the distance the light actually has to travel through it. And of course, where there's a law, there's a formula. But don't worry, this is way simpler than it looks. A is for absorbance, that's what we're measuring. C is the concentration, that's what we want to find out. L is just the path length, basically how wide the container is. And that funny little E symbol, epsilon, that's a unique number for every substance, kind of like its own personal fingerprint. So the big takeaway is, if we can measure A, we can figure out C. It's that direct. But here's where it gets really interesting. In a perfect world, this law gives us a perfect straight line relationship, just like you see on the graph. But, reality can be a little bit messy. The Lambert Law is incredibly useful, but it does have its limits. So what makes the law, bend a little? For one, if a solution is super concentrated, the molecules get crowded. They start interacting with each other, and that changes how they absorb light. Or if you have tiny particles floating around, they can scatter the light in all directions. Some samples even glow on their own, which totally messes with the readings. And sometimes the light source itself isn't perfectly pure, which can throw things off. But even with those quirks, the Lambert Law is the engine behind some amazing technology. So let's check out a device that puts this law to work every single day, the colorimeter. Okay, so what is a colorimeter? It's a machine built for one purpose, to use the Lambert Law to measure concentration. It all starts with a light source. That light passes through a slit and a lens to get a nice focused beam. Then it hits a filter, which selects just one specific color of light. And that single-colored light is what shines through our sample. The process itself is really straightforward. First, you calibrate the machine so it knows what 0 looks like. Then you pop your sample in, and that specific color of light we picked shines right through it. The sample, of course, absorbs some of that light. Whatever light makes it through to the other side hits a detector. And that detector converts the light into a number, the absorbance reading, which we can use to calculate the concentration. Simple as that. Now, colorimeters are fantastic for things that have, color. But what about all the important substances that are totally colorless? To analyze those, we have to go a step further. We need to look beyond the visible spectrum, into the world of invisible light. And this is where the spectrophotometer comes into play. You can think of it as a colorimeter on steroids. It doesn't just use the visible light that we can see, it can also use ultraviolet, or UV light. And that's a game changer because it lets us analyze a way bigger range of things, including a ton of compounds that are completely invisible to our eyes. So how does that work? Well, it all comes down to the electrons inside a molecule. When light hits them, they can absorb that energy. But here's the cool part. They're picky. They only absorb very specific amounts of energy, and when they do, they jump up to a higher energy level. By figuring out exactly which wavelengths of light a molecule likes to absorb, we can create a unique absorption spectrum for it, a fingerprint that no other molecule has. Okay, so everything we've talked about so far has been about substances absorbing light, blocking it. But what if we flip the script completely? What if we could make things produce their own light? Well, that's the science of emission, and it is a whole different ballgame. Yeah, this is a totally different way of thinking. Instead of measuring the light that doesn't get through, we're now going to measure the light that's actively being created. You can think of it like this. Absorption is like measuring the shadows,
But emission is like measuring the fireworks. So to get something to give off light, you first have to pump it full of energy. You have to excite its atoms. There are a few ways to do this. You can use a simple flame, which you might remember from a high school chemistry class. For something a bit more intense, you can use a high-temperature electric arc. Or for serious industrial work, you can zap it with a high-voltage spark.
So once the sample is glowing, the light it's giving off gets collected and passed through something that works like a prism. This awesome little device splits the light into all of its individual colors, creating a unique pattern of bright lines. It's literally a chemical barcode. A detector then reads that barcode, and just like that, we know exactly which elements are in our sample.
Okay, so we've got these two incredibly powerful methods in our analyst's toolkit, absorption and emission. But what are they actually used for out there in the real world? Let's take a look. Absorption spectroscopy is an absolute workhorse. It's used in hospitals all the time to analyze blood and urine, helping doctors diagnose all sorts of things. It's what keeps our drinking water safe by testing for contaminants. It's also crucial for quality control in the food and drug industries, making sure what's on the label is actually what you're getting. Emission spectroscopy, on the other hand, is a real powerhouse, especially in heavy industry. It's used for quality control when making metals and cement. It's also an amazing tool for protecting the environment, since it can detect tiny trace amounts of toxic metals. And in fields like forensics or geology, it can tell you the exact elemental makeup of a sample with incredible precision. So let's just boil it all down. Absorption spectroscopy is your go-to when you want to know how much of something is dissolved in a solution. It's simple, it's versatile, and it's pretty cost-effective. Emission spectroscopy is what you use when you need to know what elements are in a sample, even in teeny tiny amounts. It's super fast and incredibly sensitive. So from something as simple as a cup of tea to the chemical makeup of distant stars, spectroscopy gives us the power to read the hidden language of light. It's an incredible tool that helps us understand our world in a level of detail that's just mind-blowing. So with this power to see the unseen, what do you think we'll discover next?